Hello and welcome to my tutorial on chemical bonding. So first we're going to talk about noble gases and how they are existing as single unbonded atoms. Now the reason why this happens is that noble gases have full outer shells. So neon has 8 outer electrons, making it very, very chemically stable and therefore unreacted, and that is the common property of all of these elements along the noble gases. Period 0 or period 8 if you look at different periodic tables. So this idea of the removal and addition of electrons to the outer shell of atoms is key to the different types of bonding. So the more chemically stable your atom is, and the different kind of bonds it's going to have. Definitions are: a compound is a substance formed from 2 or more chemically bonded elements in a fixed ratio, usually shown by chemical formula like barium oxide. That's a chemical formula. And part 2, bonding. Unpaired electrons pair up by sharing or transferring electrons to form a chemical bond. This results in each turn having the same electron configuration as the noble gases. This is known as the octet rule, or the tendency to acquire a full outer shell of electrons. So basically all atoms want to have a full shell of outer electrons, and that's why they bond with other atoms, say, because they want a full outer shell of electrons. So A would bond to B because one more electron would be needed in order to complete this outer shell, say. So moving on to part 2, now ionic bonding. Electrons are transferred from the metal atom to the non-metal atom. Oppositely charged ions are formed from which they are bonded together by an electrostatic attraction. The metal ion is positive, so electrons have been removed, and the non-metal ion is negative, it has gained an electron. So an ionic bond is the electrostatic attraction between oppositely charged ions, and a giant ionic lattice is a three-dimensional structure of oppositely charged ions held together by strong ionic bonds. So in this example I'm going to have 2 sodiums overcome their ionization and due to make 2 sodium ions plus 2 electrons, and if you remember from last time, their electron configuration changes because they are now ions. So they turn from 1s2, 2s2, 2p6, 3s1 to 1s2, 2s2, 2p6 because that subshell 1 cancels when an electron is removed. And you represent all ionic bonding like this. The reason why I knew oxygen was a 2 minus, because on the periodic table is on column 6, and all column 6 atoms have a 2 minus ionic charge. I'll talk more about that on the periodic table video I'm going to do. So 2 sodium plus ions interact with the 2 oxygen, the 2 minus oxygen ion, and this forms Na sodium oxide. So the bonding is just the attraction between these 2 oppositely charged ions. Giant ionic lattices and further examples of ionic bonding. Each ion is surrounded by oppositely charged ions. These ions attract each other from other directions. each sodium plus ion surrounds 6 chlorine ions, and each chlorine ion surrounds 6 sodium plus ions. So giant ionic lattices are solid. I'll talk more about these in future tutorials, but in green I'll have the Cr minus ion, and in blue the sodium plus ion. So for every sodium one there is a chlorine one making up the lattice. Got one too many here. You should get the idea that they are weakly attracted to each other. Now if we look at another example of ionic bonding, the calcium 2 plus is formed when it overcomes its ionization energy to make calcium 2 plus ions, and then the oxygen plus the 2 electrons make it O2 minus. The 2 new electrons are represented by 2 crosses. Moving on to the fluorine now, we have aluminium 3 plus ions to make 3 fluorine minus ions in the presence of 3 fluorine atoms, and this makes aluminium trifluoride, so it'll be Al(F)(3), and the 3 plus ions and the 3 negative ions make an overall charge of 0. The attraction between these two oppositely charged ions is what keeps the compound together. And now we move on to part 4 and how their relationship is in the periodic table. So here is my periodic table from taken straight from the periodic table. So as I mentioned before, the ionic charges go from right to left on the periodic table, and the entire period has the same properties for each charge. So starting from hydrogen and helium, it's best to write hydrogen and helium on periods 1 and 2 just for the sake of simplicity. So if you have a +1 charge, you're looking at period 1, and if you have a +2 charge, you're looking at helium, and if you're looking at a +3 charge, you're looking at this period 3. For covalent, no charge here, they're all covalently bonded. And then period 5, at -1 charge, you have this one. Period 6, -2 ionic charge, and period 7, -3 ionic charge. So this is the easier ways in order to work it out in the exam, and also this number also represents the number of outer electrons in each atom in this column. So each atom in period 2 has 2 outer electrons, and there's once again another 6 in order to fill. The reason why it's 0 on this one is because there are no outer shell electrons in order to be filled on the noble gases, and that is why you sometimes see 8 on other American periodic tables or 0 here in the UK, because we forgot to break convention. You know, we're British, and that's what makes us awesome. Anyway, moving on to the next part now. Covalent bonding. In a covalent bond, an electron pair occupies the space between 2 atoms' nuclei. This attraction overcomes the repulsion between 2 oppositely charged nuclei. The shared electrons are attracted to the nuclei of both atoms sharing the electrons. So imagine that these 2 red lines are the electrons, and they are constantly repelled equally by both of the nuclei, and this electron Venn diagram has just formed, and the electrons are in the overlap of my Venn diagram permanently. The more overlap there is, then the stronger the covalent bond. So a covalent bond is a bond formed by shared pair of electrons, and the lone pair, which is here, is an outer shell pair of electrons that is not involved in chemical bonding. So if you have normally covalently bonded atoms, like same element, then the distribution of charge is equal. So the same element will happily bond together, except for the noble gases. They will not ever bond together because they have 8 electrons in their outer shell, as I mentioned earlier. But for ammonia, the nitrogen is bonded to 3 hydrogen atoms, and looking back at our periodic table, nitrogen is more electronegative than hydrogen, so nitrogen is going to have more electronegativity, but more on that in the electronegativity tutorials. For now, a covalent bond is the attraction between one metal and a non-metal, or rather 2 non-metals, and they share electrons, so one from the nitrogen and one from the hydrogen, one from the hydrogen, one from the one from the hydrogen, one from the nitrogen. It's very hard to say nitrogen and hydrogen in the same sentence. So multiple covalent bonds are quite common. You have double bonds where 2 electrons from each atom are shared, totaling 4 electrons. 4. And then you have 2 lone pairs on each one. 2 lone pairs here, 2 lone pairs here. But this time you have 8 electrons, 4 shared between each atom, in order to make a whopper triple bond. Now this is more rare, but it's nice to appreciate that triple bonds exist. And another example is when you have this. Now I've forgotten its correct chemical name, but triple bonded stuff is represented like that. But in the book, this carbon dioxide molecule is called a triple bonded molecule, although I could be wrong. Let me know in the comments below so I don't make a fool of myself. But for carbon dioxide, this also has a linear or straight molecular shape. More on that in the next tutorials. So now moving on to dative covalent bonding and Moore octet rule. So for an ammonium ion, the lone pair can be used from the nitrogen in order to bond to another hydrogen ion. So ammonia plus H plus can make a dative covalent bond in which all the electrons for the bond come from one atom. In this case it's the nitrogen. So then the ammonium ion is made when this happens, and it's usually represented with an arrow, and the electrons are never usually there when it's represented. It's usually represented like this, but I just wanted to put the electrons to show you where the electrons are going. And for elements in group 5 to 7 of the periodic table, something strange happens from period 3. More of the outer shell electrons are able to take part in bonding. One of the bonding atoms may end up with more than 8 electrons in the outer shell. Atoms of non-metals in group 5 can form 3 to 5 covalent bonds. Atoms of non-metals in group 6 can form 2, 4 or 6 covalent bonds. And atoms of non-metals in group 7 can form 1, 3, 5 or 7 covalent bonds. Now, the reason why this is because each element, like sulfur hexafluoride, for example, we'll use this example, 6 bonding pairs can form around our sulfur because there are 6 electrons on the outer shell, and the shell can then be fully occupied when it's bonded. So basically, the more electrons on the outer shell you have, the more covalent bonds you can have, as long as the atoms you are sharing your electrons with have an electron to spare, if that makes any sense. So now we're moving on to the next part, VSEPR theory, or VSEPR theory, electron pair repulsion theory in plain English. So the shape of a molecule is determined by the number of electron pairs repelling each other. All electrons have negative charges. Each electron pairs repel each other, and each electron tries to stay as far apart as possible while travelling around the orbital. These repulsions can form 3D shapes, like this one here. Methane, CH4, can form these 3D shapes, and because of the way the electrons repel each other, they always have a bond angle, which is represented here. But there are rules to this, and I will talk about them later. These lines mean that this one is in a straight linear plane. It's not going away from you or coming towards you. It's literally as drawn 2D on the paper, and this is representative. It's actually away from you, and this one is behind. It's repelling the one that's away. So the better way is to look at this 3D model, or to look on the internet for 3D chemical viewers like JMOL, and then just look up methane. In order to look at chemical databases, you need to know the chemical formula. You just type in CH4 and, for example, decane, and something that you will come up with in organic chemistry. All you have to do is type in the molecular formula, and it will come up with a representative 3D model. So playing around with models may be a good idea if you have a powerful enough computer that can handle 3D models. If not, go get a Molly-Mod kit from your chemistry teacher, because chemistry models rock, and I love playing with them. Chemistry models are very nice. But yeah, the VSEPR theory is very hard to comprehend at first, so the use of models is highly recommended by me, very highly recommended by me. So let me just draw these electron pairs repelling each other. So when you have these bonds like this, you have the bond angles that form when the like charges repel, and that's where you get 109.5 from. Now the number of bonding pairs also affects the angle. So this would be known as tetrahedral, as there are 4 bonding pairs, and 3 of them repel, and they don't all repel equally. So I'll put 4 pp for bonding pairs. They don't all repel equally, so an estimated angle would be 109.5 degrees, and that's where you get the 109.5 degrees from. So moving on to the next part now. Molecules with more bonding pairs. So more examples of shapes of molecules. This is a trigonal planar, as it has 3 bonded pairs, and good old methane has a tetrahedral shape, and it has 4 bonded pairs, and octahedral just means this is six bonded pairs and no lone pairs. If you look for the lone pairs, which there aren't any in any of these examples, then in most example questions you first off write down the number of bonded pairs, so you put 4 bonded pairs and no lone pairs. Therefore, and then you write the shape, so tetrahedral. That's a very easy way to organise your thoughts in the exam when it comes to bonded pairs. But there's always exam question practice, and I will upload more exam questions when I get my head around the questions themselves. So that's one way to do it. If you think of any other ways, then please let me know. So moving on to the next part, molecules with lone pairs and double bonds. So going back to carbon dioxide, 2 bonding regions and 2 lone pairs on each side of the oxygens can form. So the strength of electron repulsion is as follows: lone pair or lone pair is greater than bonded pairs or lone pairs, and bonded pairs is greater than bonded to bonded. So going through that again, if there are 2 lone pairs, it's weaker, but if there are 2 bonded pairs, then the electron repulsion is very strong. And looking to the right here, an ammonia molecule is pyramidal, as it has 1 lone pair and 1, 2, 3 bonded pairs, so it must have an 107-degree bond angle, and it's non-linear as it has 2 lone pairs for water, because it's only got 2 bonded pairs. It's used 2 electrons in its outer shell, and the remaining 4 electrons are repelling those 2 bonded pairs. A very good phrase to remember for this is lone pairs repel more than bonded pairs. So now we're going on to the ammonium plus ion. 4 electron pairs around the central atom, and the shape will be tetrahedral. And same thing here for the carbon dioxide. Can't have 3 oxygens bonded together. In case you noticed, it's actually meant to be a carbon dioxide atom. Just a bit neater. So this would be considered to be linear or a straight line molecule, as the lone pairs are repelling equally with the 2 bonded regions, as 4 electrons are repelling 4 electrons, so it only makes sense that they are repelling each other equally. So that's it for this tutorial. I hope you found this useful, and hope my rambling didn't put you off too much. So the basic thing to take away from this is lots and lots of practice. So we went through 1.2.5 all the way through to 1.2.10. So if you go through the textbook and go look at the questions, then they'll be quite helpful. And if you come back to my channel in future, then I will have more exam questions. So thank you for watching.